Welcome back, guys. This is question 2.13, and the statement of this question is: a pair of automotive hand lamps is connected to a 12-volt battery via the arrangement shown in figure P 2.13. So this is the figure P 2.13, and here we can see this arrangement. In the figure, the triangular symbol is used to indicate that the terminal is connected directly to the metal frame of the car. Okay, so these are basically the triangular symbols, okay, which basically denotes that these terminals or these nodes are connected to the metal frame of the car. So the part A of it is construct a circuit model using resistors and an independent voltage source, and B is identify the correspondence between the ideal circuit element and the symbol component that it represents. Okay, so this is basically a circuit, and here in order to draw it, let me first draw it as it is. So this is what this is, the battery here. This is plus, this is minus. As we have here, this battery is now connected with this switch. Okay, so let me represent this switch as this one is the switch. Okay, this is the switch. Then this is basically a node which is connected with this lamp A and lamp B as well, which means that both of these are in parallel. So therefore this switch will be here, and here we will have here this lamp A, and here at this point we have this lamp B. Okay, so let me represent it A with B, and this is the 12-volt source. Let me, this one is S, which is for switch, and these are all the bulbs here. Okay, so these are basically what? These are basically symbols which denotes that these terminals are connected with the metal frame of the car. Okay, so these are basically connected in the similar points, so therefore we can also connect them as it is here. Okay, so this is the circuit diagram, but in real world all of these elements, the cables, the switch, the battery, the lamps, all of them has the internal resistance. So therefore in order to connect them here with the real world sources and having in consideration the internal resistances of the cables and the battery as well, let me redraw it here as well. Okay, so if the internal resistance, this is the battery, okay, and let me have the internal resistance of this battery represented with R of B. So this is the internal resistance of this battery. This is plus minus. Okay, this is a switch, and switch has also the internal resistance as well. So let me represent it with R of S as well. Okay, similarly this battery is connected with this switch, so therefore this part of cable has also the resistance. Let me represent it with this RBS. So this is also the resistance RBS here as well. Okay, so these are the resistances, and then we have this switch. Okay, this is the switch. Let me represent it with this S. After this switch is connected with this lamp A and lamp B with this part of the cable, and let me represent its resistance with RA. Okay, so this is another resistance. Let me represent it with RA. Okay, then there is this lamp which has also the internal resistance. Let me represent it with what? Let me represent it with this RAA. Okay, and then this lamp here. Okay, I'm considering now it. Okay, similarly here from this to this there is also this cable here as well, and the resistance of it, let me call it what? Let me call it RBB. Okay, and then this lamp which is here as well. Okay, so these are all the resistances which are in accordance with all the cables and the elements here. Also, when these are connected with the metal frame of the car, the metal frame also has some resistance. So let me represent it with this resistance because this is RM1. Okay, this is the metal resistance, and also this one is also connected with the metal resistance as well. And let me represent it with this RM2. Okay, so these are connected here as well. Okay, so this is what, this is basically the actual diagram which shows us that this is the real world diagram, while this one is composed of these sources which are the ideal sources. This is the 12-volt source. Okay, this is the switch, this is lamp A, this is lamp B, and all the resistances here, this one, this one, this one, this one, this one, and all these ones. Okay, these are basically what, these are the resistances which basically shows us the connection between the ideal circuit elements and the resistances in accordance with all of them which are in the circuit. Okay, so that's it for today. If you have any question, if you have any ambiguity regarding the understanding of this question, you can ask me in the comment box. See you soon. Welcome back, guys. I hope all of you will be fine. So this is question 2.14 of the electric circuits by Nilsson, and the statement of this question is the terminal voltage and terminal currents were measured on the device shown in figure 2.14 as given here. Okay, so this is the figure 2.14. The value of V and I are given in the table of figure P2.14b. so this is a table for each of the current and amperes. The applied voltage V in kV is also given here. Okay, so you can see that in all of these type of circuits, this one is the independent variable, while this one, the current, is the dependent variable. Okay, use the values in the table to construct a circuit model for the device consisting of a single resistor from appendix H. Okay, so this is basically a circuit. This voltage has been applied, this is the device, and if we can draw it precisely, it is this resistor. Okay, the value of current is applied by applying the value of voltage which is here. Okay, so this is the voltage, when applied the current flows here. Okay, so in this table we can see that when the values of the voltage is applied, the current also is measured, and from it we can see that the graph of it will be like this, and it will be the ramp shape. Okay, and the slope of it will remain the same, which is the inverse of the resistor. Okay, from it we can very clearly see that according to the Ohm's law, V is equal to IR. Okay, and also the value of R here is V by I. Okay, let me put all these values here. So putting each one of this row here, we can see that V is minus 7.2 into 10⁻³ divided by minus 6. This is equal to minus 3.6 into 10⁻³ divided by minus 3. Okay, this is also equal to the 3.6 into 10⁻³ divided by 3. This is the current for this one, and 7.2. Why am I writing this 10⁻³? Because of this kilovolt. Okay, divided by 6, and this is also equal to the 10.8 into 10⁻³ divided by 9. Okay, pick any one of them and you will see the answer of it. Let me take this one, and it is what, it is 3.6 into 10⁻³ divided by 3, which is also 3600 divided by 3. Okay, which is what, which is basically 1200 ohm or 1.2 kilo ohm. Okay, so that is what, that is basically the solution of this question, where the value of this resistor is 1.2 kilo ohm. Okay, so that's it for today, in which we have seen the solution of question 2.14. In our upcoming video we will try to solve the questions which are relevant with
this question, and we will try to solve the similar question in a single video. Till then, take care of yourself, and I will see you in our upcoming video. See you soon.
Welcome back, guys. This is question 2.15, and the statement of this question is a variety of voltage source values were applied to the device shown in figure P2.15a. So this is the figure where this is the voltage source, this is the current, and device is connected with it in series. The power absorbed by the device for each of the voltage is recorded in table given in figure 2.15b. This is the table where the applied voltage is here, and the power absorbed by this device is listed here as well. Use the values in the table to construct a circuit model for the device consisting of a single resistor from appendix H. So as it is known that this is a resistor, so here for the resistor, the value of power absorbed by the resistor can be written in terms of the voltage is V squared divided by R. Okay, the only term here constant is this R, so therefore from this formula we can write the value of R is equal to V square divided by P. Okay, so all of these values, when for each of the pair here, this is pair 1 2 3 4 5 6, each of the row here will give us the constant value, and that constant value will be what, let me write it here. So that would be the R, and here it would be P, V square divided by P. So V square minus 8 whole square divided by 640 into 10 as power minus 3 for the first couple here. For the second one it would be minus 4 whole square divided by 160 into 10 as power minus 3. Why minus 3? Because this is in milliwatts. Okay, also for this one it would be 4 square divided by 160 into 10 as power minus 3. For the fifth one it would be the 8 square divided by the 640 into 10 as power minus 3, which is also equal to this 12 square divided by 1440 into 10 as power minus 3, and so on. Okay, the last one here will also be here, and that would be 16 square divided by 2560 into 10 power minus 3. So now picking any one of these values, we can find out the value of the resistor. So let me pick this one because it seems easier. So to find out the value of the resistor from it, 4 is 16 divided by the 160 multiplied by 10 power minus 3. It would be this 16 is 10 times this, and it would be 1 over 10 to the power minus 2. Okay, or this is also 10 to the power 2 or 100 ohm. Okay, so that is the value of this resistor which is here, and this circuit can also be drawn like this one. This is the circuit, this is the voltage, and the resistor here is 100 ohm. Okay, so this is the solution of question 2.15. Let me proceed to question 2.16 because that is also the relevant one, and that is here. Okay, so in this question, a variety of current source values were applied to the device shown in figure P2.16a. Okay, this is the circuit in which the voltage source is now replaced with this current source. The power absorbed by the device for each value of the current is recorded in the table which is here. The current is applied and the power absorbed by this device is here. Use the values in the table to construct a circuit model for the device consisting of a single resistor. Again, this is a single resistor, and this device can also be drawn like this one as we had previously seen, but this one is the current source. Okay, and the current source basically develops this voltage. Okay, this is the resistor as it is given, and we want to find out the value of this resistor. Okay, to find it out, again we know the power formula for the resistor, and that is in terms of the voltage which we previously seen was V square divided by R, while for the current that is P equal to I square R. Okay, so that is the
value for it. In order to find the value of r from it, this formula, so it will be p divided by I square. Okay, so that is the formula in which the only thing here in this table which will remain constant will be this r. So let me formulate it for this one. So here this r is equal to what? P divided by I square. So p is for the first pair, here is for this pair, it would be 8.25 divided by 0.5, that is equal to 33.00 divided by 1.0 for the second one. Okay, for the third one, that is also the squarish. Okay, so this is also square. Also for the others, it will be 74.25 divided by 1.5 square. Okay, and so on for the others one as well. Okay, for this we have to put it in this formula. Okay, so let us take any one of them. So let me take this one because it seems easier because of this denominator term, which is 1. So from it we can very easily see that the value of resistor is what? That is 33 ohm. Okay, and that is what? That is the value of this resistor, which is 33 ohm. You also need to keep in your mind that these denominator terms are the squarish ones. So therefore the 10 to the power minus 3, this is 10 to the power minus 3 will be here, and also in the squarish terms it will be 10 to the power minus 3, and then it will be whole square. Okay, you need to keep in your mind all of these. You have to multiply the 10 to the power minus 3 and then squarish term, because these cannot be cancelled out. One 10 to the power minus 3 will be cancelled out while the other one remain the same. So therefore the answer here we would get would not be 33, but it will be, let me solve it here. Most of the people make this mistake, so therefore I have first gone through it and now I am solving it like it is. So it will be 33 into 10 to the power minus 3 divided by the 1 into 10 to the power minus 6 because of this squarish term. So it will be what? It will be 33 divided by the 10 to the power minus 3, which is 33 into 10 to the power 3, and ultimately we will get 33 kilo ohm. Okay, so you need to keep in your mind that this is not 33 ohm. Okay, let me do it. It is not 33 ohm, while this one is the 33 kilo ohm because of the terms here. Okay, you need to keep them here because most of the people, and I have seen it in many question papers, answer sheets, in many quizzes, that people cancel them out, and the remaining term here, which is the denominator, is in the squarish form, so they forget to put them here. Okay, so that's why I have solved it here separately. So that's it for today. If you have any question, you can ask me in the comment box. See you soon.
Welcome back, guys. So this is question 2.17. So this is the figure P 2.17, and from this figure we have to find what the part A of it is. Find V naught using Kirchhoff laws and Ohm's law, and B is test the solution for V naught by verifying that the total power supplied equals the total power absorbed. Okay, so in our previous video we have seen the use of the Kirchhoff laws, the Ohm's law, and today we are going to implement it here in this circuit. Okay, so first of all, let me see that what is here. So you can see that the current which is here, this is, let me call it I naught. When it reaches this junction which is here, it splits into two direction. The first one, let me call it I2, and this one is I1. Okay, so applying here KCL, so according to the KCL, the first equation here is I naught is equal to I1 plus I2. Okay, so this is the KCL here. Similarly, here in this branch only we can apply the Ohm's law, and here
V naught is equal to what? That is I1 into R, and the value of R is 5 kilo ohm. So this is 5 kilo. Okay, let me call it equation 1 and this equation 2. Okay, the third one here is, let me consider this overall branch. Okay, this branch, let me identify it by using this overall branch. Okay, and here applying the what? Applying the KVL. If we call the voltage drop across this one as plus minus V2K, okay, and the voltage here is, let me call here, this is V naught, okay, because this is given, and this is V2K. So applying the KVL here, what will we get? V naught is equal to the voltage drop across this one, which is V2K. Okay, and here you can see that this is as that of the same polarity as here we have this V naught, because here if you see, this is here, this is minus plus 5 volts, this is V2K and V naught. Okay, so the V naught here is positive, means that it is connected to this positive terminal while this is the negative terminal. Or we can also represent it like what? It can also be represented like plus minus, which has the same polarity as that of this one. So therefore here from this one it will be subtracted because it is of the same polarity as that of V naught, so it will be minus 5 because of this 5 volts. Okay, in a single equation, it is obtained from a single equation where we had V naught plus 5 minus V2K. Okay, that is equal to 0, and that is the KVL. From this equation, ultimately the equation we got is here, this one. Okay, so let me call it equation 3. So now we have 3 equations, 1, 2 and 3. Okay, so in this equation the value of V2K is what? We can see that here this is I2, and I2 is moving through this resistor and giving us what? Then it is giving us the voltage. So therefore the value of V2K is I2 multiplied by 2K. Okay, so the value of V naught here, let me solve it. The value of V naught here is what? That is I2 multiplied by 2K minus 5. Okay, similarly the value of V naught, as we have seen, that has also the value which is here. So comparing this equation, let me call it equation 4 and 2, what will we get? Comparing them both, because the left sides of both of them are equal, so here we will get this. This is 5K, so 5K means 5000. So 5000 multiplied by I1, that is equal to, this is 2K means 2000. So 2000 multiplied by I2 minus 5. Okay, or ultimately we can also get it like moving this to the other side, 5000 I1 minus 2000 I2, that is equal to minus 5. Let me call it equation 5, and that is equation we have. Okay, so now we, which are here, the first equation is here, the second equation is here. Okay, so here in these two equations, let us compare them, and comparing them we have to put the value of I naught here as well, and using the similar color here as well. So the value of I naught is 20 milliamperes, so that is 20 into 10 to the power minus 3, that is equal to I1 plus I2, and let me call it equation 6. So now we have here this equation and equation 6, and we can find the values of I1 and I2 from those equations as well. Okay, so let us move down somehow. Okay, so as we have this equation, so let me multiply 2000 with this equation 6. What will I get here? On the right side we will get 2000 I1 plus 2000 I2, that is equal to multiplying it here at this side. What will we get? This is 10 to the power minus 3, so it will be cancelled out and we will get here 2 only, so ultimately we will get 40. Okay, again we have this equation, so let me write this equation here as well. So let me write it here. So it will be 5000 I1 minus 2000 to minus 5. So let me add both of these equations. So adding them together, these two will cancel out, and here we will get 7000 I1, that is equal to 35. From it, the value of I1 will be 35 divided by what? Divided by 7000. So it will be this 2. So 1 over 200 amps. Okay, so this is what, this is the value of I1, which is the current here. So now in order to find the value of V0, we have this equation number 2. Let me use this equation number 2. So the value of V0 will be equal to the value of I1, which is 1 over 200 multiplied by 5000. Okay, these two will cancel out and ultimately it will be here with this one. So the answer of it is 25 volts, which is the value of V0, and that is the solution of part A of our question. And in this part we have seen that how to find out the value of V0 using the Kirchhoff's laws and Ohm's law. In the part B of it, test the solution for V0 by verifying that the total power supplied equals the total power absorbed. So what are the powers which are supplied? So here we can see that this is positive, this is negative, here this is negative, this is positive, so therefore the polarity opposite of it, so we will put the negative side with it, and we will write here V multiplied by I for finding the power here. Similarly, you can see that here this is negative, this is positive, while the polarity here again is positive, negative. So therefore, as this one is also the source, so it will be minus V into I. The value of I is known, which is I2. We will find them out, and then from both of these two we can find out the value by P equal to I square R. The values of I are known and the values of R are also known. Here the value of I is I2, here the value of I is I1, both of them are known. You can find them easily. If you don't know, from this formula, you know the I1, you know the I0, you can easily find out the value of I2 as well. Okay, today we have seen that how to find out the V0 and also how to find out the total power, because here once you will find the total power developed and total power absorbed, you will see that both of them are equivalent. So if you will have any ambiguity or any difficulty in solving the question like this one, or you have any difficulty in solving part B, please let me know. I will solve it again. So that's it for today. If you have any question, you can ask me in the comment box. See you soon.
Welcome back, guys. I hope all of you will be fine. So this is question 2.17, and the statement of this question is: consider the circuit shown in figure P2.17. This is a figure. In this figure, part A of it is find V0 using Kirchhoff's laws and Ohm's law. B, test the solution for V0 by verifying that the total power supplied equals the total power absorbed. Okay, so this is the circuit, and here we have to apply the Kirchhoff laws and Ohm's law. So first of all, let us see that what is meant by Ohm's law, what is meant by the Kirchhoff's law. Okay, so let me use this green color for it. So for Ohm's law, we know that according to the Ohm's law, V is directly proportional to I. Okay, in a linear circuit, when you will increase the value of the voltage, which is the independent variable, the value of the current will also increase. Okay, so removing this proportionality sign, it will be V equal to IR, where this R is the constant, and if the resistance is constant, increasing the value of V will also increase the value of I as well. Okay, so this is what, this is Ohm's law. Also, by discussing the Kirchhoff's law, we have two laws, two very famous laws. The first one is the KVL or Kirchhoff's voltage law. The other one is the KCL, Kirchhoff's current law. Okay, so what is this? According to the KVL,
the sum of all the voltage in a loop in a branch will also be equal to 0. Okay, or we can also interpret it like that: in a branch the sum of all the voltage rises will be equal to the all voltage drops. Okay, so suppose we have here this branch, this is what, this is the resistor, this is another resistor, here we have this resistor. Okay, so if there is no voltage here, this is, let me call R1, R2, this is R3. Okay, and if we apply here the voltage source, this is V of S, this is plus, this is minus, so it will be VR1, VR2, and it will be VR3. Okay, so as these are the resistors which are the passive elements, and it always absorbs the energy, and voltage is dropped across them, so therefore it will be plus minus here, plus minus here, plus minus here. So according to the KVL here, the value of Vs will be equal to VR plus VR2 plus VR3, or ultimately we can also write it like Vs minus VR1 minus VR2 minus VR3. This must be equal to 0. Okay, so this is in the what, this is in this circuit. Suppose here if we have a branch, okay, if we have a branch like this one, many people confuses here because of it, and this is what, this is the ground one. Okay, so here we have, let me have here Vp, this is the, let me call it 1 kilo ohm resistor, and here we have this one negative positive 5 volt. Okay, so we can also apply it here the KVL as well. And what will be the KVL? As this one is a positive terminal, so it can be interpreted like that, this is positive and the other terminal here will be negative. Okay, so applying here, what we will get if we consider the direction of the current like this one, so we can see that the current is entering through this negative, coming out of this positive, so it will be Vp. Also this is the voltage dissipating device, so plus minus, so here it will be V1K. Okay, this is the voltage across it, and here again you can see that the current is entering through negative, coming out of this positive, so this is again the V5 is again the voltage drop. Okay, so and this one is what, this one is the ground one, and it is always on 0 volts, so here let me use it 0 volt and it will be equal to 0. Okay, we can always apply it to branches, to loops, to meshes, and anywhere where do you want. Okay, so this is the KVL. Also in KCL, if you want to interpret that what is KCL, so KCL says that to a node, if this is a node, if the current is moving towards it, let me call it I naught, so it will be equal to the currents which are going away from this node. Okay, so this is I1 and this is I2. Okay, so according to KCL, Kirchhoff's current law, the current moving towards a node in a circuit will always be equal to the sum of all the currents moving away from a node in a circuit. Okay, so here we can see that I naught is equal to the I1 plus I2. Okay, so here we can see that this one is here. So whatever the direction of currents here would be, we have to utilize them here as well. If the currents are moving away, so the sign of them will be positive. If these are coming towards it, it means that these are coming towards them, so therefore if all the currents are coming towards them, let me have this one, this current is coming towards it, this is also, let me I take it IB, and this is IC, so here it will be I naught plus IB plus IC, this will be equal to 0 because all the currents are moving towards this node, and that's why the summation of all the currents will be equal to 0. Okay, so that is basically the interpretation of the Ohm's law, Kirchhoff's law, KVL, KCL, and all the things which we will be using in this question. Okay, so that's it for today. Today we have seen that what is mean by Ohm's law, what is mean by the KVL, KCL, and in our next video we will try to apply them in question 2.17. Till then, take care of yourself and I will see you soon. Welcome back, guys. This is question 2.18 and the statement of it is, given this circuit shown in figure P2.18, find A, the value of IA, the value of IB, the value of V0, the power dissipated in each resistor, and the power delivered by the 50 volt source. So this is the circuit diagram. Here we have this source which is of 50 volts. 4 ohm resistor is connected in series with it, while 2 resistor 20 ohm and 80 ohm. You can see that these are connected in parallel with each other. How to see that whether these are in parallel or not? If the two legs here, you can see that the 2 points or the 2 junctions here are common in between them, and we can also draw them here as well. Okay, it is like this one. Okay, this is the source and these are the 2 common points. We can see that here this and this, these 2 legs of these 2 resistors, okay, these are connected here. So that's why these 2 are in parallel with each other, and these 2 are also in parallel with this source which is of 50 volts and 4 ohm as well. Okay, so these 3 are in parallel with each other. And what is the voltage here? This is given, this is V0 here, so therefore this V0 voltage is also here as well. Okay, so what are the currents? Let me show the currents here as well. This is IB, this is IA. Okay, and let me represent here this I0, which is the current supplied. Okay, so we can very clearly see here that this V0 is equal to the voltage across 80 ohm, across 20 ohm, and the voltage which is generated by this 50 volts minus the voltage which is subtracted by this 5 ohm. So let me call this voltage, the polarity of it will be plus minus. Why? Because this is the voltage dissipating device, and the current here is I0, and the voltage, let me call it V4. Okay, so this is the overall data we have. Now on the basis of it, what will be the points which we should know here is that the first law, and we are going to practice all those laws here. The first law is Ohm's law. Okay, so where will we apply here the Ohm's law? Here the value of V0 is equal to what? That is the current through this resistor 80 ohm and the value of this 80 ohm. So this is what? This is IB, which is this current. Okay, this is IB multiplied by this 80 ohm. Okay, why? Because V is equal to IR is the law according to Ohm's law. Similarly, this voltage, if we see that these 2 are in parallel, this is a similar voltage which is across this 2 ohm as well. So we can also write it the 20 ohm resistor multiplied by the current through it, and that is IB. This is also V0. Okay, if we want to see that what will be the voltage here, we can see that this is again V0 here as well. Okay, and that is what we have here. The second law here we are going to apply is the Kirchhoff's voltage law. Okay, so what is KVL? Let me look at this loop. Okay, when we are going to take a look at this loop, we can see that here this is, let me have this current which is I0. It is now entering through this negative terminal, coming out of this positive terminal. So this is the voltage rise. Here it is entering through this positive, coming out of this negative. This is voltage drop, and this 20 ohm resistor, and we know the voltage drop across it, and that is V0. Okay, so if we want to write the equation here, if this is Vs, so we can write here what? The KVL equation for it will be Vs, which is the voltage rise, minus V4, which is the voltage drop here, and this 20, which is again the voltage drop, and that would be minus V0. This must be equal to 0. Okay, so this is another equation which we are going to see here. And the third one here is the KCL. we are going to see here the KCL as well. This is the I naught, so I naught is going towards this node and splitting into two parts, IA and IB. So here this I naught is equal to IA plus IB, and that is Kirchhoff's current law equation. So now we have three equations. We have this equation, let me call it A. This is equation B, let me call it here B, and this is C. Okay, these three equations, or let me also call it equation A prime as well. Okay, so this is the equation A prime. So now we have these four equations, and on the basis of them, let me calculate the values. Let us compare equation A and A prime, and from it we can very clearly see that the left hand sides of both of them are equal. So that's why AIA multiplied by 20, that is equal to the IB multiplied by 80. Okay, so dividing both sides by 20, IA is equal to what? That is 4 multiplied by IB. This is another equation, let me call it 1. Okay, let me take it and put it in equation C. What will we get? Here putting it, we will get I naught is equal to, the value of A is 4IB plus IB, and from it we will get the value of I naught is 5IB, and that is what we have got. Now let me take this equation B, and from it we can clearly see that Vs minus V4 is here, this 4 ohm. So applying the Ohm's law here, I into R, so I here is I naught, so I naught multiplied by 4 and minus V naught, that is equal to 0. Now let me put all these values here. So it will be Vs is 50 because the source voltage is 50 here, minus the value of I naught is 5IB, 5 into IB into 4, and the value of V naught, we can take any of these equations. Sorry, this is A. Okay, we can take any of these equations, but as here IB is involved, so let me take equation A here. So it will be minus IB into 80, and that is equal to 0. Okay, so from it let me simplify it, and simplifying it, taking it to the other side, and this one is here, so it will be 50 is equal to 20 IB plus 80 IB. Okay, so from it we can clearly see that the value of IB will be equal to 50 divided by 100, which is 0.5 amperes. Okay, so this is what, this is the value of IB. IB is known. From this value we can put it here in equation 1 and clearly see that the value of IA will be equal to, the value of A is 4 multiplied by IB, so that is 2 amperes. Okay, so this is IA. Okay, we can take IA, IB, put them here. Okay, and from this equation the value of I naught is equal to, or the generated current, which is the total current, that will be equal to 2 plus 0.5 is 2.5 amperes, and that is what, that is the value of I naught. Okay, we can take these values, put them here, either IA, either IB. Okay, so let me put them here. If putting IB here, what will we get? Putting it here, the value of V naught is equal to what? The value of IB is 0.5 multiplied by 80. So this will be what? This will be 40 volts, and that is the value of VB. Okay, so we have found some values. So let me go to the parts of it, find the value of IA. So we have already found it out. The value of IA is here. This is part A. The value of IB, that is also found out, that is here. The value of V naught, okay, we have also found it out. This is C. Okay, the power dissipated in each resistor. Okay, so to find out the power dissipated in each resistor, let me remove some parts of it here. So let me remove it. For the power dissipation, we know the formula. To find out the power dissipated in each resistor, it will be the I square into R. Okay, to find it across 4 ohm, it will be P4. Okay, it will be I naught square into 4 ohm. The value of I naught is what? That is 2.5 whole square into 4. The value of the power dissipated at 20 ohm resistor is what? That is IA whole square into 20. Let me put the value of IA, which is 2 square into 20, and the value of the power dissipated across this 80 ohm, that is the current square, IB square, multiplied by this 80. Okay, so it will be the value of IB is what? That is 0.5 whole square into 80. You can calculate it, and then the answer of it will be here. Okay, also the power delivered by the 50 volt source. Okay, so this is the power delivered by the 50 volt source. Let me move down somehow. So part E, for the source, the value of power delivered is source current into source voltage. Okay, VI or IV, similar thing. So the current it provides is I naught, while the source voltage is 50. Okay, the current I naught, as we have found out, is 2.5 multiplied by 50. So finding it out, it will be 125 watt, and that is what? That is basically the answer of part E. If you add them all, okay, you add them all, these are the power which are dissipated in each of the resistors. You will see that the power source which is generated is equal to the power which is dissipated. Okay, so you should add them all, and all of these values will end up with 125 watt. Okay, so that's the solution of question 2.18. Today we have solved it by applying the fundamental theorems of the circuit theory. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.19, and the statement of this question is, the part A of it is, find the current I1 and I2 in the circuit in figure P2.19. So this is figure P2.19. B is find the voltage, which is here. This is the voltage V naught, and part C is verify that the total power developed equals the total power dissipated. Okay, so in order to do so, this is the circuit we have, and here we can see that this is the current source which is in parallel with this resistor, and here this resistor is in parallel with the series combination of these two resistors. You can see that this one and this one, the same current is flowing through them, so therefore these two are in series with each other. So therefore let me draw them. So in redrawing them, this is the current source, this is the resistor, or we can also draw the two series resistors as here it is. Okay, so this is the 100 ohm, this is 150, this is 250 ohm, this is the original current source which is of 1.5 amperes. So you can see that the current here is the I1, the current here is I2. Okay, as these two resistors are in series with each other, so therefore we can draw them like this is the source, this is the first resistor, and representing these two as the single resistor, we can add them together because in series the resistances have to be added together. So therefore 150 plus 250 is 400 ohm. Okay, this is 100 ohm, and the current source, the direction of it is here. This is 1.5 amperes. Okay, the polarity, the signs here are, this is the I1, this is I2. Okay, here we have this source current which is coming out of this, and this is I naught. The value of I naught is 1.5 amperes and the voltage V naught is here. Okay, so from this diagram we need to find out what we need to find all the values V naught, I1, I2 and all those values. So from it, by using the Kirchhoff's current law, here we can see that this is the node, this current is coming towards it, and it is now split it into I1 and I2. So therefore I naught is equal to I1 plus I2. Okay, and also we know the value of I naught, which is the source current, and that is 1.5 amperes. So therefore this I1 plus I2, that is equal to 1.5. let me call it equation A. Now similarly, as these two, this one and this one, these two are in parallel with each other, so therefore the voltages here between these two branches will remain the same. So therefore if the voltage across it is V1 and it is V2, so let me call it V1 is equal to V2. So the value of V1, if this is the V1, it will be I1 into 100 ohm, which is of this resistor, and V2 is I2 into what, 400. Okay, or simplifying it, we will get I1 is equal to 4I2. This is equation B, and also rearranging it, we will get I1 minus 4I2. This is equation C. Sorry, this is equal to 0. Okay, so now we have A, B and C equations. Let me multiply equation A with 4 and then add A and C together. So multiplying this equation with 4, I will get 4I1 plus 4I2, that is equal to 6. Okay, and this equation is I1 minus 4I2 is equal to 0. Let me write it here as well. So this is I1 minus 4I2 is equal to 0. Let them add together. This will be cancelled out, and here we will get 5I1 is equal to 6, or the value of I1 is 6 by 5 amperes, and that is the answer for I1. Okay, let me take this value and put it into equation B. So putting it here, I will get, this is the 4I2 is equal to I1. So putting the value of I1 here is 6 by 5. Okay, so the value of I2 will be equal to, that is 6 by 4 multiplied by 5, 6 by 20, which is 3 by 10. Okay, so this is 3 by 10 amperes, and this is for I2. In this way we have solved part A of our question, in which the value of I1 is here, the value of I2 is here as well. Okay, so as these values are known, let us find the value of V naught. As we can see that here, this branch, this branch, this branch, all these of threes are basically in parallel with each other. So therefore V1 is equal to V2 is equal to V naught. Okay, so all these three voltages are same because all these three are in parallel with each other. So let me take any of these branches and apply the Ohm's law. So let me take this branch, okay, and let me apply the Ohm's law. This is part B. So V naught is equal to V1, and the value of V1 is I1 into 100, because of V is equal to IR. So the value of I1 is known, it is here. This is 6 by 5 into 100. So it will be here, this is 20 and 120 volts. This is the value for V naught, which is the solution of part B. Similarly here, verify that the total power developed equals the total power dissipated. For it, let me move down somehow. Okay, so first of all, let me find out the power developed. So the power developed is across the source, which is here. So applying the rule here, which is P equal to IV, and here we need to find out the power which is developed. So the value of I is known, that is 1.5. okay, and the value of voltage, which is V naught here, that is also known, and we have found it out. Okay, so let me write the value 120, multiplying with it we will get what? It will be 180 watts. Okay, so this is 180 watts. Now in order to find the power which is absorbed, so we have three absorbing components. The first one is here, the second one is 150, this is 250. okay, so let me find the values of the power here. Okay, so the power which is dissipated across this one, so for it we have the formula, which is I square R or V square divided by R. We can use any one of them because the value of the voltage and current both are known, but as the current is already known and it is feasible for us to use the similar formula here, here and here, so let me use this one here. So I1 square into 100. okay, so the value of I1 is 6 by 5 whole square multiplied by 100. okay, so it will be 36 divided by 25 multiplied by 100. okay, where did I get it from? So it is written here, so it will be 144 watts. okay, so the value of P1 is known. Let me call it 2 P2. so the value of P2 is what? The value of P2 is I2 square into 150. okay, and the value of P3 is here. So as these two are connected in series, so therefore I am taking them here as well as plus I2 square, because the same current is flowing through both of them, so it will be 250. okay, so let me take this one out. So I2 square multiplied by 150 plus 250. so from here we will get P2 is equal to I2 square into 400. okay, let me move down somehow to solve it. So now P2 is the value of I2 is known, and that is 3 by 10 whole square multiplied by 400. okay, so it will be P2 is 9 divided by 100 multiplied by 400, so ultimately we will get 36 watts. okay, so from it we have got that the total power which is dissipated, that is P1 plus P2. so 144 plus 36, that is equal to 180 watts. okay, so from it we have got this 180 watts, and therefore we can see that this is the power developed while this is the dissipated power, and we can see that both of them are equal in values. okay, so what we have done today, we have solved the question 2.19, and that is what we wanted to solve today. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.20 of our book of Nilsson, and the title of the book is Electric Circuits. So the statement of the question is the current Ix in the circuit shown in figure P2.20, this is the figure, okay, is 50 milliamps. So let me write here the given data. So the current, which is I of x here, this is what? This is 50 milliamps, okay, which is what? Which is 0.05 amperes. Okay, so this is what which is given here, and also the voltage V of x is 3.5 volts. So this is V of x and the value given for it is 3.5 volts. So V of x is how much? That is 3.5 volts. So on the basis of it, we have to find I1, which is here, V1, which is here, this one, VG, which is the source voltage, and the power supplied by the source. Okay, so this is the source, the power supplied by it. Okay, so in order to solve it, we have to keep one thing in our mind, that if we have any component, either a passive component or an active component, there are three quantities associated with it. So what are those three quantities? Those are V, I, and R, okay, which are voltage, current, and resistor for the linear element. Okay, so if any two of them are given, we can find out the third one very easily. Okay, so let us solve our question, and in solving it, let us first proceed with this one, and we can see that I1 is the current which flows through 200 ohm and 175 ohm as well, because these two are in series with each other. So therefore the voltage value is known, which is across it, and the resistor is also known. So we can very easily find out the value of current, because the voltage and resistors are known. So we can find out the value of I1. So from it, the part 1, which is I1, that is what? That is V divided by R by the Ohm's law, which is V equal to IR. Okay, so let me put the values here. The value of V, that is V of x, that is known, and that is 3.5 divided by R, which is how much? That is 175. Okay, so let me solve it, and after solving it, the value for it is 20 milliamps, and that is the solution of part A of my question. In part B, we need to find out the value for V1. Okay, V1 is unknown, and here we can see that if we can see this node, the current Ix is coming here and then splitting into two components, where this one is I1 and let me call this one as I2. So therefore applying KCL here, we can very easily see that I of x, which is the current coming towards this node, is equal to the I1 plus I2. Okay, or from it, the value of I2, which is flowing through this branch, through this 250 ohm resistor, that is I2 is equal to Ix minus I1. Okay, so the value of Ix is known, that is 50 milliamps, and the value of I1 is also known. So let me put them here. The value of Ix is 50 milliamps, and the value of I1 is 20 milliamps. Okay, from it I can get 30 milliamps. After finding out this I2, we can see that here, this is the resistor across which we have to find out the value of V1. The value of current is known, which is 30 milliamps, and the value of resistance is 250. So let me find out the value of V1, that is 250 multiplied by I2. Okay, so that would be 250 multiplied by 30 multiplied by 10 to the power minus 3 due to this one. So solving it, we will get 7.5 volts. So that is what? 7.5 volts is the value of the voltage across this 250 ohm. So we have found it out, and that is the solution of part B. In part C, we have to find out the value of V of G, and here in this loop, let us use the what, let us use here the KVL, and applying KVL here, I can very easily see that the value of Vg is equal to what? That is equal to the value across this 50 ohm resistor. So in this loop, we can see that this is V50, and V50 is the voltage drop across this 50 ohm resistor plus this V1. Okay, so plus this V1. Do we know the value of V50? No, we don't know it, but we know the value of the resistor. We know the value of the current which is given. So we can very easily find out the value of V50, that is Ix multiplied by 50 ohm. So let me put these values, that is 50 multiplied by 50 multiplied by 10 to the power minus 3. Okay, so this would be 2.5 volts. Okay, so the voltage here is given. Let me write these voltages here. So V50 is 2.5 volts. The value of V1 is 7.5 volts. So adding them together, I will get 10 volts. Okay, so that is what? That is the solution of part C. In part D, I have to find the power supplied by the voltage source. So in order to find the power supplied by the voltage source, let me solve it here. That is the power supplied by this Vg, that would be Vg multiplied by the current which is going through it, and that is I of x. Okay, so the value of Vg is known. The value of Vg is 10, and the value of I of x is 50 milliamps, so 10 to the power minus 3. So ultimately we will get what? It will be 0.5 watts, what we have found out. Okay, so that's what, that is basically the solution of question 2.20. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.21 of our book Electric Circuits by Nilsson, and the statement of this question is the current IA in the circuit shown in figure P2.21, this is the figure P2.21, is 2 milliamps. Okay, this is the IA, and the value of IA is 2 milliamps. Okay, so on the basis of it, we have to find what? We have to find the value of I naught. This is I naught. The value of Ig, this is Ig, and see the power delivered by the independent current source. This is the current source. We have to find the power delivered by this one. Okay, so let us start it, and in starting it, we have to find different quantities, and let me solve it here. So solution of it. Okay, so first let me have here the KCL. So according to the current Kirchhoff's current law, here this current is flowing towards this node which is here, and let me call it node A, and here the current which is flowing towards it is Ig. Okay, and then it divides into two currents. The first one here is I naught, and the second one here is Ia. So according to the KCL, Ig is equal to what? That is equal to I naught plus Ia. Okay, here we just know the value of I of A. Okay, this current is known, and this is the similar current which has been flowing through all these three resistors, because these three resistors are in series. When these three resistors are in series, we have to find the equivalent resistance of that, and that would be the 1 kilo ohm resistor plus 4 kilo ohm resistor and plus 3 kilo ohm resistor. So ultimately we will get the 8 kilo ohm resistance. Okay, so this is the equivalent resistance here, and here if we can see the equivalent of it, we can see that here these two resistances, where this is the equivalent resistance, this is the 2 kilo ohm resistance, and here we have this current source. These three are in what? These three are in parallel with each other. This is the I of G, and from it this current is flowing, this is here, this one is here, and this is here. Okay, so let me have here, this is A, and let me call the voltage across it as VA. So this is the same voltage which is here and here as well. Okay, so this is the same voltage. If we can find out the value of this VA, which is here and here as well, we can find out the value of current here as well. Okay, so let me first find the value of VA, and the value of VA is what? That is this IA, which is flowing through all of these resistances. So IA multiplied by this equivalent resistance, which is here, because this is I of A. Let me put these values here. The value of I is given, and that is 2 milliamps. Okay, so that is 2 into 10⁻³ and the equivalent resistance here is 8 kilo ohm. So that is 8 into 10⁻³. These two will cancel out, and ultimately here we will get what? The voltage here is 16 volts, and that is V of A. So let me take this one here. If this voltage is known, this is known, this is known, and this is also known, so from it we can very easily find out the value of this current, which is I naught. Okay, why? Because with each of the passive element we have three quantities associated, which are voltage, current, and resistance. If two of them are known, we can easily find out the third one. So here this resistance is known, the voltage is known, we can very easily find out the value of I naught. So using the Ohm's law, okay, the value of I naught is what? That is the value of VA divided by the resistance, that is 2 kilo ohm. Okay, so let me put these values here. So this is 16 divided by 2 kilo. So ultimately the answer of it is 8 milliamps. Okay, so the value of I naught is known, and that is 8 milliamps. Okay, so I naught is already known. So from this formula, if the value of I naught is known, the value of I is already known, so we can very easily find out the value of IG. So the value of IG is what? I naught is 8 milliamps, IA is 2 milliamps, so that is 10 milliamps. Okay, so that is what? That is basically the solution of part B. Okay, so this is part B, this is part A. Okay, now we want to find out the power delivered by this source. Okay, so now for the sources, we know that, let me solve it here. For the sources, we know that the power which is generated or dissipated is equal to V is equal to V multiplied by I, where V is the voltage across the source and I is the current provided by it. So the voltage which is here is already VA, because all of these three are in parallel, and the current is IG. Okay, so let me put all these values. So it will be 16 multiplied by this 10, okay, into 10⁻³ because this is the milliamps, so it will be 160 milliwatts, and that is what? That is the solution of part C of my question. Okay, so that's it for today, in which we have seen that by employing the concepts of the series circuits, by using the KCL, by using the Ohm's law, and then applying the concept of the power generated or dissipated by the voltage or current source, we have solved this question. If you have any question, you can ask me in the comment box. See you soon.
Welcome back, guys. So this is question 2.22, and the statement of this question is the current I naught in the circuit in figure P2.22 is 1 amperes. Okay, so I naught, which is this current, this is how much? This is 1 ampere. So let me write it here. The value of I naught is 1 amperes. Okay, so on the basis of it, we have to find I naught,
which is here. Okay, we have to find the power dissipated in each resistor. Okay, we have to find the power dissipated in each resistor, and we have to keep it in our mind that the power dissipation formula in each of the resistor here is P of R is equal to IR square multiplied by the value of the resistor. Okay, so for that we will need what? We will need the value of the current which is flowing through each of the resistor here. Okay, so let me indicate the currents which we want to find and which we had to find out. So the first one here is I naught, which is already available. The other ones are this, let me call it I4, because it is going through or passing through this 4 ohm. Similarly, let me call it I10. Okay, this current which is flowing through this one, this is I25. Okay, and let me call the current which is flowing through this source, that is Ig, or the current from this source. Okay, so these are the currents which we want to find out. And what other currents we want to find out? According to the part A, I want to find out I1. Okay, similarly here I4. Okay, similarly Ig, which is here. Okay, similarly I10. These are the currents we want to find out, and this last one, that is I25, we want to find them out. Okay, so let us start and let me find them out. So first of all, we can see here that the voltage here, which is what? The voltage here is 150 volts if we consider this one as the ground, and on the ground we have here the 0 volt. So the voltage here is 150, and let me call here at this point the voltage equal to VB, and the voltage here is VA. Why this? Because I want to find out the currents, and I have told you that with each of the element here we have 3 quantities associated. Those are voltage, current, and the resistance. If any 2 of them are known, the third one can be easily found out. So if the voltages are known, we can easily find out the currents here. So first of all, we can see here that the voltage here is, let me call it V50, which has been dissipated across this 50 ohm resistor. So we can very clearly see that the value of V50 is 50 multiplied by I naught. The value of I naught is known, and that is 1 ampere. So therefore the value of V50 is 50 volts. Okay, so therefore if this voltage is 50 volts, from here we can very clearly see that this is the first voltage, this is the second voltage. So we can see here that 150, which is this voltage, minus this VB, that is equal to what? That is basically the V50. Okay, as the value of V50 is known, so therefore the value of VB would be equal to what? That would be 150 minus V50. So therefore this is 150 minus 50. So ultimately the answer of it is 100 volts. So the value of VB is 100 volts, which has been known. So this value is now known. Why this? Because this is the potential difference. If we have a resistor here and we want to find out, this is VB, this is VA, and if I want to find out the voltage across this resistor, this is what? This is, this VR is equal to VB minus VA, and that is what? That is the potential difference formula, and this is what I have applied here in this branch. Okay, so this is 100 volts and this is already known. So in order to find out the current here in this branch, and we can see that here this is VB and the voltage is known, so the current I25 is 100 volts, which is VB, divided by 25. So the value of it is 4 amperes. Okay, so this value is known, and that is 4 ampere. So let me write it here. This value is 4 ampere. This is known. Now here we can see that this is the current which is coming towards is, this is also the current which is coming toward this node as well. So therefore applying KCL here at VB, we can clearly see that I10 plus I0, that is equal to the I25, which are the currents coming towards the node, is equal to the currents coming away from the node. Okay, so here the I10 is unknown while I0 is known, which is 1, sorry, this is plus, and also the value of I25 is 4. So therefore on the basis of it, this I10 is 3 amperes. Okay, so I10 is 3 ampere. Let me write it here as well. Okay, so these two currents are known now. Now in order to find the I4, IG and I1, I must have this VA. Okay, in order to find the value of this VA, let me move down somehow. Okay, here, so in order to find the value of this one, I can very clearly see that here applying KCL at VA, we can see that I4 is equal to I1 plus I10. Okay, the value of I10 is what? This is the current which is moving in this direction, so that therefore this is VA minus VB divided by 10. Okay, so the value of I10 is known. The value of I4 is what? That is 150 minus VA divided by 4. Okay, so let me write them here. 150 minus VA divided by this resistance, which is 4, potential difference divided by the resistance is equal to the current. Okay, so this is the formula I have applied here. Similarly for I1, I can see that this is VA divided by 65. Okay, so that is what? I1. So VA divided by 65, which is I1, and also the value of I10, which is already known, and that is 3. Okay, once this will be solved, we will get the value of VA equal to what? VA is equal to 130 volts. So this is what we can find out from here. When you will solve this equation, this is a linear equation, only one thing is unknown, and that is this VA. When you will solve it, you will get 130. So, okay, so as from this formula, we can clearly see that the value of I1 is here, and the value of I1 is equal to VA divided by 65. So the value of VA is 130 divided by 65. So we will get 2 amperes. So the value of I1 is 2 amperes. Okay, so the value of IA is known. Similarly, from this formula, which is this KCL, we can put the value of I1, we can put the value of I10. So the value of I10 is 3, the value of I1 is 2, so 2 plus 3 is 5. So therefore here this is 5 amperes. Okay, so these currents are known. Now the value of IG, we can see that this is IG, and here to this node this I1 is coming, and this I25 is coming towards this one. So therefore let me write it here. IG is equal to the I1 plus I25. Okay, let me put their values. The value of I1 is 2, the value of I25 is 4, so this is 6 ampere. So therefore this is 6 ampere. Okay, so we can see that all the currents are known, and we have all the currents, we have found them out, and now you can apply the formula which we have already seen here, and you can find it out. From this formula you can find out all the power dissipated in all the resistors. So let me first find out it across this 4 ohm resistor, and let me use this color. So across this 4 ohm resistor I will have P4 is equal to I4 square into 4, the value of I4 is 5. So 5 square multiplied by 4, so it would be 100 watt. Okay, so P4 is 100 watt. Similarly, you can find it out for this one, for this one, for this one, for this one, and all the others one by using this formula. And at the end, when you will add them together, you will see that these would be equal to the power generated by this 150 volt source, and the power generated by this 150 is equal to what? That is Ig multiplied by 150. Okay, so Ig is already known, that is here. You have to put this value here, multiply them with 150, and when the power dissipated by all of these resistors will be added together, it will be equal to what? It will be equal to 6 multiplied by 150, and that is 900 watts. Okay, so that's it for today. The most crucial part here was finding all the currents which are here. Let me underline them. So these are all the currents which are the most crucial part we had to do here. So that's it for today. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.23 of the book Electric Circuits by Nilsson and Riedel, and the statement of this question is: the variable resistor R in this circuit in figure P2.23, this is the figure P2.23, is adjusted until I naught equals 10 amperes. This is I naught which is flowing through this 5 kilo ohm resistor. Find the value of R for which this current, when it is adjusted, this current is 10 milliamps. Okay, so we have to find this resistance. This is the variable resistor, and with the help of the knob or anything else, this is adjusted in such a way that the current which is flowing through this 5 kilo ohm is what? This is 10 milliamps. Okay, so the only quantity which we have now is this I naught, and the value of I naught is 10 milliamps. Okay, so if this is 10 milliamps, let us have here this voltage, let me call it V naught. So the current through this resistor is known, that is 10 milliamps, and the value of the resistance is also known. So we can very easily find out the value of V naught, that is I naught multiplied by 5 kilo ohm. So 5 kilo ohm is 5 into 10 to the power 3. So let me put these values. I naught is 10 milliamps, so 10 to 10 to the power minus 3 multiplied by 5 into 10 to the power 3. These two will cancel out, and here V naught is 50 volts. Okay, so the value of V naught is known, and that is 15 volts. Let me, okay, so this is the V naught. Apart from it, another quantities which are known are here. We have, let me call it VA. At each of the node, let me identify the voltages, and let me call it VB. Okay, this is, let me call it the ground one, and the voltage here is 0. Okay, so the value of VA, which is from this source, and we can see that this is VA minus 0 minus 80. So the value of VA is 80 volts. So the value of VA is also known, and that is 80 volts. Okay, so if this value is 80 volts, this value is known. So if we have this scenario that we have here Vx, here we have Vy, and certain voltage R, we can find out the current through it by the formula, which is I is equal to the potential difference divided by the resistor. So the potential difference here is Vx minus Vy divided by R. Okay, so let me apply the similar formula here, and in applying it, let me have this current here, let me call it I 1.5. Okay, so the value of I 1.5 is the potential difference, which is VA minus V naught divided by 1.5 kilo. So let me put these values here. So the value of VA is 80, the value of V naught is 50, and the value of the resistance in between them is 1.5 kilo. Okay, so it would be 30 divided by 1.5 kilo. So we can find it out, and it will be 20 milliamps. Okay, the value of this current is also known, and that is 20 milliamps. Okay, so this is known. Now at this junction we can see that this current, which is 1.5, is coming towards it, and it is now splitting into two parts, which one is I naught, the other one is going through this 3 kilo ohm resistor. Let me call it I3. Okay, so by applying KCL here, okay, if I will apply KCL here, I can very easily see that, let me use this black color for it. Here I can very easily see that I1.5 is equal to I naught plus I3. Okay, the only unknown current here is I3, so I3 can be found out by I1.5 minus I naught. Okay, let me put these values. So I1.5 is known, that is 20 milliamps, and I naught is also known, that is 10 milliamps, so 10 milliamps. Okay, so the value of I3 is now 10 milliamps. This current is also known. Let me underline it as well. So these currents are known. Let me remove this one. So these things are now known. Now this current is here. We can very easily find out the voltage across it. So V3K, let me have this voltage here across this one, and it would be what? It would be I3 multiplied by 3K. So I3 is known, that is 10 milliamps. So 10 into 10 to the power minus 3 into 3 into 10 to the power 3. These two will cancel out, and we will get here 30 volts, which is across this one. Okay, so this is again the voltage which is known. So from it, now we know this voltage, we know the consumed voltage as well. We can very easily find out this voltage now. So from the formulation and from the potential difference formulation, we know that V naught minus VB, which is the potential applied and the potential which is remaining, that is equal to the consumed power, which is across this 3K. Okay, so from it we only don't know this VB, so VB is equal to what? That is V naught minus V3K. The value of V naught is known, that is 50. The value of V3K is also known, that is 30. So this is here. So from it the value of VB is 20 volts, which is here. Okay, so this is the 20 volts, and again this one is known. Now when this voltage is known, the potential difference is known, the resistance is known, we can very easily find out this current. Let me call it I5. Okay, by applying the formula, which is the potential difference across this resistor divided by the resistance. So applying it with here, we will get I5 is equal to the VB divided by 500. Okay, the value of VB is also known, that is 20. So 20 divided by 500, and applying it, it will be 1 over 25. So ultimately this is 40 milliamps. Okay, so the value of I5 is also known, and that is 40 milliamps. Okay, so when this one is known, what is the objective of finding it here? We need to find out the potential difference here, which is VR. We need to find out the current here, that is IR. If these two quantities are known, we can very easily find out the third quantity. So let me call here this IR. If IR is coming towards this node and this I3 is coming towards this node, these are combined together and give me this I5. So again applying at this node the KCL, what will I get here? Let me use this color. So applying KCL here, it will be I5 is equal to I3 plus IR. Okay, I5 is known. Yes, I5 is known, and that is 40 milliamps. Okay, the value of I3 is known. Yes, that is 10 milliamps. So the value of IR is I5 minus I3. Let me put these values. So I5 is 40 milliamps okay, and the value of I3 is 10 milliamps. Okay, so we will get 30 milliamps here, and that is the value of the current which is flowing through this resistor. This IR is known. Now in order to find the value of VR, we have two voltages across it. One is this VA, the other one is this VB, and from the potential difference formula we know that, let me use this color, we know that VR, which is the potential difference across this resistor, or that is the voltage which is consumed across this resistor, that is equal to the applied voltage minus VB, which is the remaining voltage. So VA is 80 volts, which we have found in the very start, and the value of VB, let me see that where is VB. So it is VB, so that is 20 volts. So we will get here, this is the value of the voltage across this resistor is what? That is 60 volts. Okay, so now we have this VR, we have this IR, both of them are known. I have told you that with each passive component we have three quantities relevant with each other. One is the current, the other one is voltage, and the third one is the resistance. If two of them are known, we can very easily find out the third one. So let me solve it here. Okay, let me solve it here, and by applying the Ohm's law we can see that R is equal to VR divided by IR. Okay, the value of VR is known, that is 60. The value of IR is 30 into 10 to the power minus 3. So solving it and finding all the values, we will get it 2 kilo ohm, and that is what? That is basically the solution of our question. So what we have done, so initially in order to find out the value of this R for the current which is here, and the value of current was known, that current should be 10 milliamps, we had to find out the value of the potential difference and the value of the current which is flowing through this resistor. So for finding it out, we have found out all the voltages, all the node voltages, all the branch currents in this circuit, and ultimately we have found out the value of this resistor should be at 2 kilo ohm, so that it can provide me the value of I naught equal to 10 milliamps. So that is the solution of our question 2.23. If you have any question regarding the solution of our question, you can ask me in the comment box. See you soon. Welcome back, guys. So this is question 2.24 of our book Electric Circuits by Nilsson, and the statement of our question is for the circuit shown in figure P2.24. So this is the figure, and here we have to find a R. Okay, so this is R, we have to find it, and after finding it out, the part B of it is the power supplied by the 250 volt source. The only source here is this voltage source, and the power supplied by it we have to find it as well. Okay, so let us first write here the given data. So this is the 24 volts, and this current which is flowing through this 5 ohm resistor is known. When this is the source voltage, so we can see that it is connected here at these 2 points. So therefore the voltage here in these, between these 2 points, is 250 volts. So therefore if we consider this one at 0, so this one will be here, will be 240 volts. Okay, similarly in order to find out the voltage here, if this is the supplied voltage, this some voltage will be consumed here across this 5 ohm resistor, and we will get the voltage which is here. Okay, similarly this is the current, this is 4 amps current, and we can see that this 5 ohm, this 10 ohm, these two are in series, so the same current has been flowing through both of them. Okay, so let me find out the voltage here. So let me call it this VA. In order to find the voltage here, the originally applied voltage is 240 volts. So the remaining voltage which will be here would be what? It would be 240, which is the supplied one, minus the voltage which is across this 5 ohm plus the voltage which is consumed by this 10 ohm. Okay, so these are the two voltages. Let me find them, so it will be 240 minus this will be I5 multiplied by 5, which is according to the Ohm's law, and similarly here this one will be I10 multiplied by the 10 ohm, which is this resistance. Okay, we can see here very clearly that I5 is equal to the I10, and this is, as these two are in series, so therefore this is 4 amps. So let me write these values. So it will be 240 minus, let me take it out, so this 4 is here and this 5 plus 10 is 15, so here it will be, so it is now 240 minus this is 60, so the value of VA is what? That is 180 volts. Okay, so the value here is 180 volts. So now this voltage is known, this is already known, so we can clearly see that this is the current which is flowing through this branch. If the potential difference is known, we can very clearly and easily find out this current, and let me call this current as I of X. Okay, so this I of X is VA minus 0, which is this voltage, divided by the resistances, which are 14 plus 6, so this is 20. Okay, so it will be 180 divided by 20, these two will cancel out and it will be 9 amps. Okay, so this current is the 9 amps. The current which is coming towards this one is 4 amps, this one is 9 amps, so therefore this is also the current which is coming towards this node as well. Okay, so if we apply the KCL here, let me apply the KCL and let me call this current as IY. So therefore, according to KVL, IY plus 4 ampere is equal to the IX. Okay, or the value of IY is equal to IX, which is 9 minus 4, so this IY is 5 amperes. Okay, this is the current which we know now. So at this point we know all these currents, these are known. So when we have found out this current, we can very easily calculate the potential drop here across this one. So here this is V of 4, so V4 is 4 multiplied by IY. Okay, so 4 multiplied by 5, so this is 20 volts. When this voltage is known, so this which is the applied one here can also be found out, and let me call it V of B. Okay, so let me call it VB. This is VB. So how to find it out? We can see that this VB minus VA will also be equal to the voltage which has been consumed here, and this is the original rule which we have applied here, because this is the applied one, this is the remaining one, so the consumed one will be here. So we can find it out. VB minus VA is equal to V4. Okay, let me write here all the values. So VB is equal to V4 plus VA. So V4 is how much? We have found it out, that is 20 volts. VA is how much? That is 180 volts. So this is now 200 volts. So this voltage is also known. What else do we have to find out? The potential difference across this R can be very easily found out by this one. Okay, so we have seen that this potential difference would be what? It would be 240 minus VB will be equal to VR. Let me write these values. So 240 minus VB, which is 200. Okay, so the value of VR would be here, and ultimately the value of VR would be 40 volts. Okay, so one thing is known here. The other thing which we have to find here is this I of R. Okay, so because once VR and IR would be found out, we will be easily finding out the value of R, that is VR divided by IR. We will be using this formula. These two are known, but the IR is still unknown. So therefore, if this is the current which is the applied one, or this is the same current which is going through here, if this is known, we can see that this is the 4 amps and the remaining one would be here. We can find it out as well. But here at this junction, we can see that this is the current, this one is also the current. So we have to find out these two currents. Let me call it I1. So here I1 plus Ix, that is equal to Ig, which is this current. But the value of I1 is still unknown. So therefore, the voltage VB is known. The potential difference across this 10 ohm is also known, and the resistance is also known. So therefore, the value of I1 is VB minus 0 divided by 10, which is 200 divided by 10. So that is 20 amps. Okay, taking it and putting it here, the value of Ig would be equal to, the value of I1 is 20. The value of Ix is how much? That is 9. So we can clearly find out the value of Ig, which is 29 amps. Okay, so this value is also known. So this is Ig. 4 ampere is coming towards this 5 ohm, and the remaining one will be flowing through this R. So applying KCL, we will very easily find out the current through it, and that would be the 25 amperes. Okay, so the value of IR is 25. The value of VR is how much? That is 240 minus 200, that is 40 divided by 25. So finding it out, we will get what? The value of R would be 1.6 amperes. So this is the value of the resistance which we had to find out. So the part A is solved now. Now in order to find the solution of this part B, which is the power supplied by this 240 volt source. So therefore, in order to do so, let me use this color. So here the power supplied is equal to I multiplied by V. The I which is flowing through this one is Ig. The value of it is already known, and that is 29. And the value of V is, which is the voltage source, 240. Multiplying them, we will get 6960 watts. And that is the solution of part B of our question. Okay, so that's it for today, in which we have seen the solution of question 2.24. If you have any question, you can ask me in the comment box. See you soon.
Welcome back, guys. So this is question 2.25, and the statement of this question is the voltage across the 16 ohm resistor in the circuit in figure P2.25 is 80 volts. Okay, so this is the 16 ohm resistor, and the voltage given is this one, and the polarity of it is as here. So which is positive at the upper terminal, which we have described. So on the basis of this statement, what do we have to find out? The part A of it is find the power dissipated in each resistor. Okay, these are 1, 2, 3, 4, 5 resistors, and we have to find out the power dissipated in each of the resistor. Find the power supplied by the 125 volt ideal voltage source. Okay, so this is the ideal voltage source, and the power supplied by it, we have to find it out. And in last, we have to verify that the power supplied equals the total power dissipated. Okay, so that is what, that is the circuit, and we have to find out the quantities given here. Okay, first of all, we have to find out the power dissipated in each resistor, and we have to keep it in our mind that the power consumed by each of the resistor can be found out in terms of the voltage. It would be V square divided by R, or in terms of the current, it will be IR square into R. Okay, so these are the two formulas which we can use for the resistors here. But here, in order to look for it, we can do what? We can see that in order to find out these quantities, the resistances are given, which are 7 ohm, 15, 5, 30 and 16, but the values of the currents are not given. Okay, similarly the voltages are not given as well. You can use any one of
these formulas and find it out, but here we are going to use this one, and therefore I will find out the value of the current through each of the resistor here. Okay, so first of all, let me redraw the circuit. This circuit is basically can be redrawn as, this is the circuit, these points are the common one in between this source and these two resistors, and here this one is the common one. Here we can see that the voltage here is 125 volt, and here let me call it 0 volts. Okay, so at one terminal of it is what, 125, the other one is 0, so therefore the total voltage here in between these 2 points is 125 volt, which is due to this voltage source. So here this is plus minus 125, also as this is the common point in between them, so therefore this is here, the first resistor is here. Okay, the second one which is shorted here, this one is here, and the resistances which is here is connected here. Similarly, with this point we have this resistor as well, this is the 30 ohm resistor. Okay, with this point we have the 16 ohm. Okay, we can see that, let me write their values as well. So 15, 7 ohm, 5 ohm, 30, and this one is 16, and here we can see that these two are connected, so therefore let me connect them, and these are also connected with the negative terminal of this source. Okay, so this is the circuit which we are going to solve right now. So let me choose this black color for it, and here the voltage given is this plus minus 80 volts. Okay, and the current which is flowing through this 16 ohm resistor 8, let me call it I subscript 16. Okay, similarly the current which is flowing towards this node is IG, which is the source current. Okay, this split into two currents. The first one is the I15, which is flowing through this 15 ohm resistor, and the second one is I7, which is flowing through this 7 ohm resistor. Okay, and by going through all of this we will find out the values of IR from this circuit, and then we will apply this formula. So let us first find out this I16, because with each of the passive elements we have three quantities interrelated. The first one is the resistance, the second one is the current, the third one is the voltage. If any two of them are known, the third one can be easily found out. Okay, so with it, this resistance is known, this voltage is known, so we can clearly and easily find out this I16. So let me write here the quantities which I want to find out. So let me first write the quantities here for my own convenience. Let me use this one. So I have to find out I of G. Okay, similarly I of 7, I15. Okay, and I of 5 as well. Okay, I15, I5, then I30. Let me write it here, I30, and the last one is I16. So for I16, let me move down somehow. This is I16. Okay, so these are the currents we have to find out here. Okay, and again selecting the same black color here. Here the value of I16 is what? The value of I16 is 80 volts, which is the voltage, divided by the resistance, which is 16, and this is from the Ohm's law, which is V equal to IR, and from it we can clearly see that this is 5 amps. Okay, so I16 is where? This is here, so this is known, and that is 5 amps. Okay, now as this current is known and this voltage is also known, we can see that we have already known that the voltage here was 125 volts. Okay, so at this point the voltage is 125, so therefore this is also 125. So this voltage is 80, this is 125, so the potential difference is known here, which is 125 minus 80. Okay, as the potential difference is known, we can divide it over this 15 as well, and then dividing it we will get the value of I15. Okay, so finding it out, it will be 45 divided by 15, that is I15, and the value of it is 3 amps. Okay, so the value of I15 is 3 amps. This is already known here. So when this current is known, which is coming towards this node, and let me find out this I5, which is also coming towards this node. So these two, I15, I5, are coming towards this one, and these are combined together, and then cumulatively these are giving me I16. So let me apply the KCL here. Okay, according to the KCL, I5 plus I15, that is equal to I16, or as we want to find out this I5, so I5 is equal to I16 minus I15. The value of I16 is how much? The value of I16 is 5. The value of I15 is 3. So therefore the value of it is 2 amperes. So I5 is 2 amperes, that is here. Okay, so when this current is known, the resistance of it is already known, and we can easily find out the voltage drop across it. So that voltage is, let me call it V5, and in order to find that voltage, it will be the current, which is I5 multiplied by the resistance, which is 5. So I5 is 2, the resistance is 5, it is 10 volts. Okay, so this V5 is 10 volts. Let me call the voltage at this point V0. Okay, so the potential difference across this resistance is what? That is V0 minus the voltage here, which is 80. So now if this one is the applied voltage, this is the voltage which has been remained after the voltage which is consumed from it. So this is what? This is the consumed voltage. So therefore V0 minus 80, which is the voltage which is remaining here, this is the applied voltage, this is equal to what? This is the voltage which is consumed. Okay, so if we want to find out the value of V0, it will be V5 plus 80. The value of V5 is how much? The value of V5 is 10 plus 80, that is 90. Okay, so the value of voltage at this point is 90. Now from it we can find out the current I30 as well, because this voltage is known, that says 0 because of this voltage is known, which is 90. So potential difference divided by the resistance, it will be what? It will be I30. So potential difference is V0 minus 0 divided by 30. So V0 is 90 divided by 30, so that is 3 amps. So the value of I30 is 3 amperes. Okay, this current is also known. Now the only remaining current is this I7. Again, the potential or the voltage at this point is known, the potential at this point is known. So 125 minus V0 divided by 7 will be I7. So the value of I7 is what? Sorry, let me write it somewhere else. So let me write it here. So I7 is potential which is at the upper point, that is 125, the lower point voltage, that is 90, divided by 7. Sorry, so the value of it is 35 divided by 7, so that is 5 amperes. So the value of I7 is 5 amperes. All of these currents are known. This is the supplied voltage current which is coming towards this node, and then it is split it into I15 and I7. So let me apply the KCL here. So applying KCL, we can very easily see that Ig is equal to I7 plus I15. Let me write their values. So I7 is how much? That is 5. I15 is how much? That is 3. So that is 8 amps. So that is 8 amperes. Now all the currents which we wanted to find out are known now. Okay, so these are all the currents, and now these are the resistances, because this is the source current, and for finding the source voltage we can use the formula P equal to IV. The current of it is known, the voltage is known, so voltage is V, the current is 8, we can find it out, and 125 multiplied by 8 we will get the answer, and that is 1 kilowatt or 1000. You can multiply it and you will see that it is 1000 watt. Similarly, for this one, this is the 7 ohm resistor across which 5 amps is flowing. So to find out the power across it, let me call it P7. It will be I square into R. Okay, for it will be P15, and the current through it is 3 square into 15. For this one it will be P5, so it will be I square into R, which is 5. For it is P30. It is now 3 square into R, which is 30, and for this one let me have here P16. It will be 5 square into 16. Let me calculate them. So P7 is 5,525. So let me calculate them. It is 25 multiplied by 7, that is 175 watt across 7 ohm resistor. For P15 it is now 339 915 135 watts. Okay, and also this P5, this is 224 45 20 watts. P5 is 20 watts. Okay, P30 is 339 93 27, so this is 270 watts. And this one, which is P16, that is 5525 25 multiplied by 16 is 25 multiplied by 16 is 400. Okay, so that is 400 watts. So let me now add them all together. So adding them all together, this is 400 plus 270, okay, plus this one now 20, plus this is 135, plus, and this one 175. So the answer of it is 1000, which is the total power consumed or the dissipated by all these resistors. Okay, adding them all together, you have got that the dissipated power is 1000 watts. Okay, which is part A. In part B, we have also already found out the value of the applied power, and in part C we have to see that whether these two are equivalent or not. So we have verified that the supplied power is 1000 watt and the consumed power is also 1000 watts. Okay, so that's it for today, in which we have seen the solution of question 2.25. If you have any question, you can ask me in the comment box. See you soon. Welcome back, guys. I hope all of you will be fine. So this is question 2.26 of our book, which is Electric Circuit by Nilsson, and the statement of this question is the current IA and IB in circuit in figure 2.26, which is this one, this is the figure, are 4 amperes and minus 2 amperes. Okay, so where is IA and IB? We can see here that this is IA, okay, and the value of it is 4 amperes. Okay, let me write it here. IA is 4 amperes, and the value of IB, which is this current, that is minus 2 amperes. If the direction of it is here in this one, and this is what, this is minus 2A, so if the current is in the other direction like this one, if this is IB, so the only sign of it will be changed while the magnitude or the value of it will remain the same. So if I take this IB as IB prime here, so the value of IB prime is what, that is 2 amperes from the value of IB, which was minus 2 amperes. Okay, so from it we have got this IB prime. So you have got my point that if this was minus negative, so in the opposite direction the current will be of the same magnitude while the direction of it has been changed. Okay, so on the basis of it we have to find what? We have to find I of G, V of G. So this is I of G, this is V of G, and also find the power dissipated in each resistor. And I have previously told you that to find the power dissipated in each resistor here, that would be PR IR square multiplied by R. Okay, so this is one of the formula on the basis of the currents, on the basis of the voltage. That formula is VR square divided by R. So we can use any one of them, but here probably we will use this one, and for it the values of the resistors are given. What we have to find out are the currents in all of these resistors, and the part D of it is show that the power delivered by the current source is equal to the power absorbed by all the other elements. So means that this current source is the main power delivering element here. Okay, so now let us start it, and here let me first see that what are the things which are given. So first of all, let me point out some voltages and currents here. So the first, let me take this point, this point, this point. Okay, let me call this as the VA. Okay, this one as VB, and this one as VG, which is already given. It will be the ground, which is here, and the currents here, which are, let me take this current as I of B. This current taking the direction here, this is I30. Okay, this is this one, and the current which is flowing through this one, that is I5. Okay, these currents are given now. Now on the basis of our solution here, let me solve them all here. So first of all, let me find the value of V of A. As we can see that the current direction is in this way, that is IA. So therefore the polarity of it will be what? That would be plus minus here. Okay, because this is the passive element, and in passive element always the voltage will be dropped. So in voltage drop, the polarity should be like it is from positive to negative. Okay, in this way VA will be what? If we apply the KVL here in this branch from it to this one, from VA to this one, in this branch it will be what? It will be VA is equal to 100 volts because of this voltage source, and we can see that these are the same polarities which are connected. So therefore it will be V15. Okay, the voltage drop across this 15 ohm resistor. So it will be VA 100 plus V15 is IA multiplied by 15, and the value of IA is also given, that is 4. So 4 multiplied by 15, and ultimately we will get the value of it is 160 volts. Okay, so this value is the value of VA is given now. Now in order to find the value of the VB, what do we have to do? We must have all these values. Okay, so here we can see that this is VA, this is VB, this is the applied voltage, while this one is the remaining voltage, while the consumed voltage will be consumed across this 9 ohm, 11 ohm, 10 ohm. So we can apply here what? We can again apply here the KVL. Let me apply here the KVL. So here it will be VA minus VB, which is the applied, minus the remaining, is equal to what? That would be the V9 voltage drop across this one, plus the voltage drop across this 11 ohm, plus the voltage drop across this 10 ohm resistor. Okay, so let me apply them. The value of VA is known. Yes, that is 160 minus the value of VB. The value of V9 is IB prime multiplied by 9, the value of V11 is IB prime multiplied by 11, and the value of V10 is IB prime multiplied by 10. So therefore IB prime is common in between all of them, so that is IB prime, and the values of the resistors by applying the Ohm's law here. Okay, so 9 plus 11 plus 10. Okay, so it is 160 minus VB, the value of IB prime is 2, multiplied by, it is now 30. Okay, so 160 minus VB, that is equal to the 60. Okay, finding it out, the value of VB is now what? That is 160 minus 60, so that is now VB is 100 volts. Okay, so the value of VB is also known. So this one, this voltage is now 100 volts. This is now 160 volts. These voltages are known. Now when this voltage is known, this is 0, we can find out this current, which is IB, that would be the potential difference divided by the resistors. So therefore the value of IB is what? That is VB minus 0 divided by the resistances, which are 4 plus 16, 20. Okay, so the value of VB is 100 divided by 20, so that is 5 amperes. Okay, so the value of IB is 5 amperes. Now in order to find the value of I30, we can see here that there are two currents which are coming towards this junction or this point. These currents are IB prime, I30, and when these are combined together, it will give me this IB. Okay, so IB is equal to the I30 plus IB prime. Let me write their values. So the value of IB minus IB prime, that is I30. Okay, to find out the value of I30, let me write the value of IB, that is known, and that is 5 amperes, minus the value of IB prime, that is 2. So the value of I30 is 3 amperes. Okay, this current is now already known. Now this current is known, and to find out the value of this current, which is I5, what do we have to do? We must have the potential difference, which is VA minus VG. But now here, in order to find out this VG, we have this potential drop, we have this voltage. So again, applying the same formulation what we have applied here, we can write here what? We can write here VG minus VB divided by the 30, that is equal to I30. Okay, we can see that this is the potential difference divided by the resistance, that is equal to current. Now in order to find the value of the VG, it will be VG is equal to what? That is 30 multiplied by I30. Okay, and VB will be added with it, so that would be VB. Okay, so 30 multiplied by I30 is 3. Okay, plus VB, so VB is 100. Yes, so that would be the value of VG is now what? Let me calculate it. So this is 90 plus 100, that is 190 volts. Okay, so the value of VG is 190 volts. Now when this voltage is known, we need to find out the current, which is I of G. In order to find out the current here, we need to find out this current, which is I of 5. Okay, so in order to find the value of I of 5, this voltage is known, this voltage is known, so potential difference divided by the resistance, that is I5. Okay, so let me write it here. So the value of I5 is VA minus VG divided by the 5 ohm, that is VA is 160 minus 190 divided by 5, so it will be minus 30 divided by 5, so that is minus 6 amperes. The value of I5 is minus 6 amperes. So when this current is coming towards this one, it is split it into two parts. One is I30, the other one is IG. So applying KCL here, let me use this point. At this point, we can see that I5 is equal to what? That is IG plus I30. Okay, the value of IG is not known while the other values are known. So therefore, the value of IG we have to find out, and that would be I5 minus I30. The value of I5 is what? That is minus 6, and the value of I30, that is already known, that is 3. So minus 3. So from it we can find out the value of IG, that is minus 9 amperes. Okay, so the value of IG is known, the value of VG is known. To find out the other power dissipated in each resistor, we have to find the currents, and these are known. This current is known, this current is known, okay, this current is known, this is known, this is known, all these currents are known. Okay, we can see that here we have found out all these currents. So applying this formula, we can find out the currents. Okay, for the last part, it is your assignment to see that whether this is the prime source or not. For the hint, for the sources, we can find out the formulation, and that is P is equal to IV. That is what? That is the power dissipated or developed formula for the sources, which are two sources here. One is the voltage source and the other one is the current source. If you have any question, you can ask me, and I will solve the part D of it as well in my next video. Okay, so that's it for today. If you guys have any question regarding the solution of this problem, you can ask me in the comment box. See you soon.